Hello everyone! Thanks so much for joining us today for another webinar on real-time simulation and hardware-in-the-loop testing with the RTDS Simulator. Today we are talking about distribution system simulation and the closed-loop testing of distribution automation equipment. We will have a demonstration with an intelligent fault interrupter or Recloser, the IntelliRupter from S&C Electric. My name is Katie Sidwall from RTDS Technologies, and I'll start us off today with some housekeeping notes and a brief presentation, some background on distribution mode in the RTDS simulator, and then I'll pass it off to our application specialist, Christian Jeggs, for the presentation and demo. I wanted to mention that the demonstration today is using our software RSCAD version 5, which is what you are accustomed to seeing. But as you may have seen on our social media and our YouTube channel, we recently announced that we are releasing an all-new updated software for the RTDS simulator. It's called RSCAD FX, and it has a totally overhauled look and feel, improved ease of use, and quite a lot of new features. So if you haven't seen it yet, take a look at the teaser video for RSCAD FX on our YouTube channel. And once the software is released, we will be doing a webinar showing off the new features and allowing users to ask some questions. So look forward to that, and I hope to see you all there. Please feel free to submit your questions today throughout the webinar. You don't need to wait until the end. Please submit them via the Q&A panel, and we will get to those questions throughout the presentation. Then we'll do a live Q&A section at the end where we will flesh out some of those answers and try to get to some of the questions that we couldn't address during the presentation. We will also be releasing a Q&A document with the recording of this webinar. So those will be made available on our website next week, and we will let you all know by email, everyone who's registered, when the recording and the document are ready. So I'm going to spend a little less time on introductory information on the company and on the technology background today, and more time talking about distribution applications. So if you're totally new to the RTDS simulator and you'd like to learn more, I encourage you to visit our website, and you can always email marketing@rtds.com if you have any general questions. So the RTDS simulator is an electromagnetic transient simulation tool, or EMT, and it runs those EMT simulations in real time. What differentiates EMT simulation from other power system simulation approaches, like phasor-based solutions, is that it provides a time-varying instantaneous value output. So the simulation output gives you a waveform like the one shown here, which would ideally match the current or voltage waveform if it were to be measured from the real system. And this allows for a greater depth of analysis over a wider frequency range and the ability to reproduce fast transients on the power system, such as faults on the distribution system. And the higher the sampling frequency of the simulation, the higher frequency results you can accurately reproduce. The period of the sampling frequency, or the distance between two consecutive outputs, is called the simulation time step. So the time step that is necessary for a given simulation depends on the phenomena of interest to the user and the bandwidth that is required to accurately represent those phenomena. The typical time step for the RTDS simulator has historically been in the 50 microsecond range, but there are scenarios where a smaller or a larger time step is appropriate. When we say the simulation takes place in real time, we mean the computer needs to solve all of the equations for the network in real-world time equal to or less than the simulation time step. And this means that the real time for a power system event to occur is equal to the simulated time. So that is really what differs from offline EMT simulation programs, which run on standard PCs. The simulations can take a lot more than, or sometimes less than, the real event time, depending on the complexity of the case. So that's one of the advantages of real-time simulation. It's the speed and the efficiency. And that really comes into play when many iterative tests need to be done, or slower dynamics over a long time period need to be included in the simulation. The unique advantage, though, of running simulations in real time is the ability to connect external hardware to the simulation and test it in a closed loop. So closing the loop means not only observing the response of a protection or control device to an imposed signal, but also interfacing the external device's response back into the simulated network. And this type of testing, also called hardware in the loop or HIL testing, is only possible if we are updating the inputs and outputs of our simulation continuously in real time. It's not possible with an offline modeling tool or with open loop testing tools like a relay test set. And it also allows for multiple devices to be tested at once, more systems level testing, which is increasingly necessary for predicting vulnerabilities in equipment in the modern system. The original application for real-time simulation was HVDC control testing, but the applications have expanded significantly, and one of the big application transitions we've seen is that while it was originally mainly used for transmission system simulation and device testing, the RTDS simulator is increasingly used for distribution level applications, like you see in the top left area here. And there are a couple of special considerations for this type of testing, which I will get into in a moment, and that has actually affected the design of the RTDS simulator a little bit. So here's a non-exhaustive list of examples of distribution-related applications that we've seen with the RTDS. There is the HIL testing of distribution control devices like volt-var optimization systems, advanced reclosers, capacitor bank control, voltage regulator control, real-time automation controllers, bay control, network reconfiguration systems. The list goes on. There's also the testing of power plant controllers, or PPCs, by which I mean higher level power controllers for solar PV systems or other distributed generation systems. And that testing could be from a manufacturer's acceptance testing perspective or from a network operator's integration testing perspective, or a combination of the two. Distribution energy resource management systems, or DERMS systems. This might mean there's a software in the loop component to the testing. And distribution protection, whether it's a feeder protection relay, transformer protection, or what have you. There's also power hardware in the loop testing, where actual power devices are connected in a closed loop with the simulation via a 4-quadrant amplifier. And this can be used for inverter testing at the distribution level. And finally, outside the hardware in the loop application, real-time EMT simulation can be used for operational studies for distribution systems, understanding system performance with a high penetration of renewables with the detail offered by EMT, the ability to simulate and study low-level controls and fast transients. If you're not familiar with our hardware, I wanted to show it quickly before Christian gets into the demo with it. So Christian will be using our NovaCore hardware, which is our current generation of simulation hardware based on the IBM Power8 processor. And we use this hardware because we need a dedicated parallel processing system to maintain an EMT simulation in real time. And we achieve modularity using a core licensing system. So the IEEE 123 node distribution system, for example, with no modifications, requires a single core to simulate on NovaCore. And we're using a modified version of this case for today's demo that Christian will show you. In addition to the actual simulation hardware solving our circuit, we also require I/O devices to create a closed-loop testbed for our automation equipment. So today's demo uses an analog output card to send values from the simulated network to the S&C IntelliRupter. And for digital I/O, we have a panel integrated into the front of our simulator cubicle, which is used for logic level input and output. And that is driven by our GTFPI, or front panel interface card. Christian will show in more detail what the setup looks like momentarily. We also have communication protocol-based I/O, which is commonly used in distribution automation, whether that is using the Modbus protocol for power set points from a PPC to a simulated generator, IEC 61850 for protection testing, or the SCADA protocols or generic socket integration for DERMS system testing. We won't be using these for testing the IntelliRupter today, as it relies on traditional analog and digital I/O. Before passing it over to Christian, I want to talk a little bit about distribution simulation. So the original application of this technology was HVDC control testing, and the simulation of traditional transmission system models is really what drove some of the early design decisions for the RTDS, from a modeling, a user interface, and a solver perspective. That being said, it has always been possible to simulate distribution systems. There have never been restrictions to the voltage level or the circuit topology that you are simulating with the RTDS, and the I/O is generic. So for a long time, it's been theoretically possible to do something like Recloser control testing with the RTDS simulator. However, as we saw more and more customers with a big focus on distribution simulation, we made some changes to the simulator capabilities based on some common characteristics of the distribution networks that customers were simulating. So typically, these systems have a larger number of nodes in one tightly coupled area with relatively short transmission lines. So no lines long enough to mathematically decouple the system into subsystems. Typically, the circuit topology is radial rather than the meshed configuration that is more typical of transmission systems. So that means less components connected to each power system node. And in turn, that means even though we have more nodes in our network admittance matrix, it is much more sparsely populated. And that has implications from a processing perspective. One other thing to note is that these systems often have a combination of single-phase, 2- and 3-phase components, so there's a need for easy phase breakout and access to multi-phase components. So distribution mode is our solution to cater specifically to networks with these characteristics. And when you switch to distribution mode in the RSCAD software, as is done for the demo in today's webinar, there is a much higher node limit than is possible in normal simulation mode, so you can simulate larger networks. And we're able to increase the network size capability because of a few factors, one being the radial nature of the network, and the other being a relaxed time step. So the minimum time step in distribution mode is 100 microseconds. And the idea is that for these applications, the phenomenon of interest can still be represented with accuracy at this slightly larger time step. So there's no negative impact on representing the transient behavior. Distribution mode has a limited subset of components. So when you're in distribution mode, you can only access some of the master library components. It's a pretty large subset, but some of the notable exclusions are switched power electronic models, because we can't interface to smaller time steps in distribution mode. So instead of the fully switched converter models, averaged models of power converters can be used in distribution mode. And that's normally acceptable given the higher level nature of the controls that we're typically testing. Another exclusion is traveling wave transmission lines. There are no traveling wave models in distribution mode, only pi section lines, which is generally acceptable anyways, given the shorter nature of lines that exist in those cases. And another thing to note is that some components, including pi section lines and variable loads, have reduced load units in distribution mode. So what that really means is, in addition to a higher node limit, a higher number of these components can actually be placed in the case. And I'll mention too that distribution mode has full I/O capabilities: analog, digital, and communication protocol-based I/O. I think an important takeaway about distribution simulation with the RTDS simulator is that distribution systems can absolutely be simulated in regular simulation mode, and vice versa for that matter. Technically, you could represent a portion of a transmission system in distribution mode as well, as long as it met the restrictions, the requirements. The voltage levels are really arbitrary, and the I/O is generic. Distribution mode was just developed in order to help simulate larger feeder models on a given configuration of RTDS simulator hardware if the circuit is a good candidate. If it has some of these traits and it's a good fit, then distribution mode can be a big advantage to the user. Lastly, we have a conversion tool for SIM's SimDist software. It's a third-party distribution system simulation software that's popular in the US, so you can directly import cases from this tool into RSCAD. And when we rolled this out, we also released special stretchable components, which make it easier to lay out a converted distribution case and to break out into other phase configurations. That won't be shown in today's demo, but if you do join us for our RSCAD FX software webinar, I can show that off a little bit. Okay, so that gives you some background on distribution simulation. I'll pass it off now to Christian to give you a closer look at the IntelliRupter and at our HIL setup for the day.
Hi everyone, my name is Christian Jeggs and I'm one of the application engineers here at RTDS Technologies. And today I'm going to be giving you a presentation on hardware and loop testing for a fault interrupter with a distribution feeder model. Just a brief outline of today's presentation. I'm going to start by laying out some of the motivation and context for this type of testing. I'm also going to cover some basic details about the IntelliRupter PulseCloser fault interrupter from S&C Electric. Then I'll cover how the IntelliRupter is interfaced with the RTDS hardware, and I'll also briefly talk about the distribution system that's going to be simulated on the RTDS in today's demonstration. First, a little bit of motivation and context. When it comes to distribution systems, faults are always a major concern. Faults on the distribution system can impact the reliability of the distribution system and result in outages and equipment damage, which both result in increased costs for utilities. However, the majority of faults on the distribution system are temporary, and up until now, industry has relied on the use of reclosers in order to clear these faults and prevent sustained outages. Let's have a quick look at how these conventional reclosers work. Upon detecting the presence of a fault, the recloser will operate the circuit breaker in order to disconnect the faulted portion of the circuit. Then after some time, the recloser will reclose the breaker in an attempt to restore power. However, if the fault is still present, the recloser will repeat this reclosing process up to 3 or 4 times in an attempt to try and clear the fault. If the fault persists, then during this reclosing process, the recloser is subjecting the distribution network to the full fault current during each reclose attempt. This can result in damage to distribution system equipment and also causes wear and tear on substation transformers due to the mechanical forces on the winding from the resulting fault current. The IntelliRupter PulseCloser fault interrupter from S&C Electric Company uses a different approach. The IntelliRupter uses its patented pulse closing technology, which uses a small pulse of current to try and detect the presence of the fault prior to reclosing. This small pulse of current subjects the distribution system equipment to less stress compared to conventional reclosers. More detailed information about the IntelliRupter can be found on S&C Electric's website in the link shown here. This slide here shows an overview of the construction of the IntelliRupter. You can see that the IntelliRupter can be mounted to a power pole using a bracket, and the remainder of the IntelliRupter equipment is mounted on the stainless steel base. This equipment includes things such as disconnects, power modules, integrated voltage sensors, and surge arresters. The stainless steel base also has a connection for a control module, and it's the control module that contains all of the protection and control algorithms used in the IntelliRupter. Now, in order to test the IntelliRupter with the RTDS simulator, what we need to do is disconnect this control module from the IntelliRupter and use it for our testing with the RTDS. In order to test the control module from the IntelliRupter with the RTDS simulator, two additional hardware components are required. First hardware component is the docking station module from S&C Electric. This is shown on the right-hand side of the figure. The docking station is what allows the user's PC to communicate and program the control module. The user will use the Intellilink software in order to communicate with the docking station, which is then able to program the control module. The second hardware component that's required is the IntelliRupter Test Interface Unit. Now, the IntelliRupter Test Interface Unit provides two separate functions. First, it allows for the interconnection between the IntelliRupter control module and the docking station. Second, it also allows for an interconnection to the RTDS simulator in order to exchange analog signals and binary inputs and outputs with the RTDS, which are required for testing the IntelliRupter. Now, there are two different types of IntelliRupter test interface units available for use with the RTDS. The first is the Omicron RI-R1 S&C IntelliRupter testing package, shown on the top of the slide. The second test interface unit is from Doble, the Doble F5850 IntelliRupter PulseCloser testing interface. The pictures on the right-hand side show how both of these test interface units are used with the RTDS simulator. Now, in this demonstration, we're going to be focusing on the Omicron RI-R1 test interface unit. So the rest of the slides will pertain to details for this particular test unit. This slide here shows the hardware interface between the IntelliRupter and the RTDS simulator. Recall that we're going to be simulating the distribution network on the RTDS by using the NovaCore chassis. And then what we'd like to do is we'd like to interface this simulated distribution system with the IntelliRupter controls. In order to do this, we not only need to use the Omicron RI-R1 IntelliRupter test interface, but we also need to use the input and output cards from the RTDS simulator. In this example, we're going to be using the analog output card, or GTAO card, as well as the front panel interface card, or the GTFPI card. The IntelliRupter is going to be operating a breaker contained within the simulated distribution system in order to perform the pulse closing. In order for the IntelliRupter to do that, the IntelliRupter needs information about the voltage sensed on either side of the breaker and also the current flow through the breaker. Now, these signals are going to be provided to the IntelliRupter by using the analog output card of the RTDS simulator. The outputs of the analog output card are then connected into the LL-out 1 through 6 and 7 through 12 inputs on the Omicron RI-R1 test interface. This allows for these signals to be injected into the IntelliRupter. Next, the IntelliRupter needs to exchange various binary input and output signals with the RTDS simulator in order to actually actuate the breaker to perform the pulse closing operations. Now, in order to do this, we interconnect these binary inputs and outputs by using the GTFPI card. So the GTFPI card is interconnected with the binary inputs and outputs cable from the Omicron RI-R1 test interface. This then allows for the RTDS simulator to exchange these binary inputs and outputs with the IntelliRupter. This slide here shows a complete test setup with all of the necessary hardware. On the right-hand side, we can see the protection and control module from the IntelliRupter, and we can see it's connected to the Omicron RI-R1 test interface unit, which is also connected to the S&C Electric docking station. Now, the RI-R1 unit from Omicron is also connected to the RTDS simulator by using the I/O cards on this table here. These I/O cards are connected into the front of the Omicron RI-R1 test interface. The distribution system is simulated on the NovaCore simulator, and the user's PC is shown on the left-hand side here. The user can use their PC to not only manipulate the simulation executing on the NovaCore, they can also use it to operate the Intellilink software, which communicates with the IntelliRupter. Lastly, I'd like to briefly talk about the distribution system that's going to be simulated on the RTDS. In this demonstration, we're going to be simulating the IEEE 123 bus distribution system. The Intellirupter is going to be interfaced with one of the breakers within this distribution system, and it will use this breaker in order to perform its pulse closing. Now, this system represents a typical distribution feeder and contains overhead and underground lines, unbalanced load, and the typical voltage drop problems that you find in distribution systems. These voltage drop problems are then addressed but through the use of shunt capacitors and voltage regulators. This network is a good candidate for distribution mode on the RTDS because of its radial line segments, and it doesn't require any detailed switching models for power electronics. In a system like this, the transient behavior will not be significantly impacted by the slightly larger simulation time step that's used in distribution mode. Here are some of the references used in today's presentation. So that ends today's presentation. Enjoy the rest of the demonstration.
Today I'm going to be giving you a demonstration that shows how one can use the RTDS simulator to test the S&C IntelliRupter fault interrupter. So the first thing I'm going to do is navigate to my program files directory here, locate the S&C Electric directory, and launch the Intellilink software. This is the software that allows me to connect my PC to the IntelliRupter. So I'll go ahead and log in here with the default credentials. Okay, so I've launched the Intellilink software and my PC is now connected to the IntelliRupter, and this is where I can access all of the various settings and logs of the IntelliRupter. Just go here and clear the warnings from the previous use. And next what we'll do is launch the RSCAD software. And I'll launch the draft case that we're going to be using to test the IntelliRupter. So this is the draft case that we're going to be using for the test with the IntelliRupter. This is the IEEE 123 bus system, and it's modeled in our distribution mode environment. So if we have a look at the circuit options for this case, we can see that the simulation time step in this case is 130 microseconds. Now we have detailed documentation on this IEEE 123 bus case, so I'm not going to talk too much about the layout of the system. What I'd like to do in this demonstration is focus on how the IntelliRupter is interfaced with the RTDS and how we can use the RTDS to test the IntelliRupter. So there wasn't really any changes to the original IEEE 123 bus case other than what was added in this hierarchy box here for the IntelliRupter. So let's go ahead and open that up and have a look. Okay, so here we can see the contents of the hierarchy box. In the top left-hand side, we notice that we have our bus 18 and bus 135 connections here, and those are shown here as well. So these two buses are what connect zone 2 and zone 3 together through this breaker. And this is the breaker here that connects buses 18 to 135, and this is the breaker that the Intellirupter is going to be operating for any of its fault interrupting or reclose operations. Okay, so let's just go through some of the different elements that were added in order to accommodate the Intellirupter, first starting with the Rogowski coil. So in order to test the Intellirupter, what we're going to need to do is we're going to need to provide the Intellirupter with information about the source side voltages, the load side voltages, and also the currents passing through the breaker. Now, the currents are normally sensed by means of using a Rogowski coil. So what we're doing here is modeling that Rogowski coil. So if we have a look here, we're passing the three-phase currents through these washout components. And what we've done with these washout blocks is we've actually set the gain and the time constants of these components so that this washout block behaves like a derivative. So you can see that I have a very large gain, which actually cancels out with this time constant. So in the numerator, we're just going to have this S term. While in the denominator, since the time constant is very small, this 1 plus st can be approximated as just 1. So this washout block is now essentially a derivative term. So we use this component to get the derivative terms for the currents. We multiply by the mutual inductance of the Rogowski coil, and that's how we get the Rogowski coil voltages. Okay. So it's the Rogowski coil voltages that are going to be used that allows the Intellirupter to sense the information about the currents flowing through the breaker. Okay. So just a little bit about the hardware for this test setup. What we're going to be doing is we're going to be sending out the voltages on either side of the breaker out of this GTAO component, as well as the Rogowski coil voltages. Now those signals are going to be sent from the GTAO card, and they're going to be connected to a separate test interface for the Intellirupter from Omicron, and it's known as the Omicron RI-R1 test interface. So these signals will go into the Omicron test interface and then be injected into the Intellirupter equipment. Okay. We also have some logic signals that are going to be returned from the Intellirupter equipment, and those logic signals will also be provided via the Omicron RI-R1 test interface. Here we'll be connecting the binary inputs from that test interface to the front panel interface card. We do that by means of a terminal block, and then we can bring those logic signals in, and we're going to be using those logic signals to operate this breaker here according to the Intellirupter. Okay. So we also have some breaker controls here that take the signals from the Intellirupter and translate those into the close and trip commands for this breaker here. Now, in order to test the pulse closing functionality of the Intellirupter, what we'd like to do is subject the system to a fault. So we have some fault controls here that will allow us to control the point on wave of the fault, the duration of the fault, the type of fault, and so on. So that's really the only components that are added. So one more thing I could add here is, we have a breaker here, and then we have this zone 3 feeder where we have a bunch of lines and loads here. And then this breaker at the end of the feeder is normally open. So we have a radial feeder here with a bunch of lines and loads. Now, the lines all have inductance in them. And what happens is when the breaker operates, we suddenly interrupt the current that's flowing through those inductances. And that can lead to what's known as chatter. Okay, so this is a numerical oscillation that can come from this type of simulation. And what we do is we add some shunt capacitance here just to suppress that numerical chatter. Okay, so those are really the only components that have been added to the system. The other thing I'll note for you is in the downstream feeder here in zone 3, we've added this fault component at bus 47. And what we're going to be doing is subjecting this feeder to a fault so that we can verify the pulse closing functionality of the Intellirupter. So let's go ahead and compile this case. So the case is compiled successfully. Let's just have a quick look at the hardware requirements. So here we could see a case that's running on 2 cores of a NovaCore chassis here. So this concludes the portion of the demonstration here in Draft. Next, let's move on to the runtime environment. Okay, so we've now launched the runtime environment for the IEEE 123 bus system that we're going to be using to test the S&C fault interrupter. So I'd just like to give you an overview of the layout of the case here in runtime. So the first thing we can see is we have a little graphical layout of the various buses and lines in the IEEE 123 bus case. So there's a bunch of group components here where we can actually open them up and and there's some meters in here where we can look at the RMS voltages at for each of the phases. We also have some breaker icons here, and these breaker icons will actually use the breaker logic from the case to display the status of the breaker. Red indicating a closed breaker and green indicating an open breaker. Okay, so we've positioned our Intellirupter at this breaker here between buses 18 and 135. So I've included a kind of a close-up view of that portion of the system down here that may be a little bit easier to work with. Now we also have our sliders and our dials for our fault controls that we can use to configure the fault later on. So now let's do a little split screen view here between the Intellilink software and the RSCAD case here. And let's go ahead and start the simulation here. So we notice the signals in the Intellilink software are all showing all zeros for the source side voltage, load side voltage, and the currents. However, now that we've started the simulation, we can see the Intellirupter breaker is open. The breaker in the simulation is also open. However, now we have some voltage on the source side of the breaker, and we can see that in the Intellilink software as well. So the next thing we'd like to do, I guess first we could also note that on the load side of the breaker there's no voltage because the breaker is open. And there's also no current flowing through the breaker because, again, the breaker is open. We see the same information displayed on the Intellilink software. Okay, so the next thing we'd like to do is actually close this breaker, and we can do that by using this close button from the Intellirupter. Now, before I do that, what I'd like to do is actually arm the plots in the runtime environment so that we can observe that close operation taking place. So I've pushed this arm external plot update button. Now I'm going to have the Intellirupter issue the close command for the breakers. Okay, so the Intellirupter closes the breakers. You can see the plots are updating. And if we have a look at our meters here, we can now see voltage on the load side of the breaker. We see the breakers are now red because the breakers are closed. We can also see some current flowing through the breakers here. Now, if we have a look at the Intellilink software, we can see that same information there. So we not only have voltage on the source side of the breaker, but also on the load side of the breaker. We also see some current flowing through each of the 3 phases in the Intellirupter. You know, the values of the voltages sensed, the voltages and the current sensed by the Intellirupter match those shown on the meters in the simulation. The other thing we can note is that the Intellirupter is indicating that the power flows from source to load, which is the same as what we have in the simulation here. Okay, if we have a look at the plots that are updating here, we can see we have the close and open commands from the Intellirupter for each of the 3 phases. And we can see here the Intellirupter issuing the close commands. Once the breaker is closed, these open signals are all going low. So it's closing all 3 phases A, B, and C. So we can go ahead and zoom in here to have a closer look at that. So these signals are being sent by the IntelliRupter and they're brought into the RTDS simulation through the front panel interface. So we see A phase, B phase, and C phase closing here. We have the voltages, load side first the source side voltages, load side voltages, and the current through the breaker. Okay, next what we'd like to do is test the pulse closing functionality of the IntelliRupter. Now, before we do that, I'd like to show you how these pulse closing tests are actually set up in the IntelliRupter. So if we go in the Intellilink software and we have a look at the protection tab under the setup menu and general profile number 1, here we can see the time over current curves that we've selected for either direction here. We're not going to focus too much on this. What I'd like to focus on is this tab here that says testing after initial trip. And this tab here displays the various tests that will be performed after a trip is issued. Okay, so what we can see here is that we've configured 4 tests, test 1, 2, 3, and 4. And these tests are all time delayed from one another. So once we have our initial trip, test 1 will occur 0.2 seconds later. After test 1, test 2 occurs 1.8 seconds later, and so on for test 3 and test 4. So these tests is where the pulse closing is going to be occurring. So you can see that we've configured the pulse close sequence here. So the IntelliRupter is going to be performing this pulse closing to check to see if the line is still faulted. Now, if the IntelliRupter determines that the line is not faulted, then it'll proceed with reclosing the breaker. So now in the simulation here, what we'd like to do is we'd like to configure our fault such that we can test the pulse closing algorithm of the IntelliRupter. So what we can do is we can configure a point on wave of 0 degrees, a fault duration of 60 cycles, and this dial here allows me to set the fault type. Now currently I have the dial set to 1, which will mean an A phase to ground fault, single line to ground fault. Now a 60 cycle fault amounts to a fault duration of 1 second. So this is going to be useful for our test with the IntelliRupter because during that 1 second we expect the IntelliRupter will trip based on the time over current characteristics, and that test 1 will then be performed. Well, when test 1 occurs, the fault will still be present because this 1 second duration will have not elapsed yet. So then we can observe the pulse closing action of the IntelliRupter during a faulted condition. Next, 1.8 seconds later, test 2 will occur. Now 1.8 seconds later, the fault will no longer be present, so we'll be able to again observe the pulse closing operation once the fault is no longer present. So this is what we're hoping to observe in this demonstration. Now before we apply the fault, what I'd like to do is go to the logs menu and first clear the history log. This way, once we initiate the fault, we can view all the logs that are generated by the IntelliRupter. Okay, now when I push this button here, I'll simulate that fault at bus 47 and we'll be able to observe the operation of the IntelliRupter. Now during this operation, you'll see the plots will be updating to capture all the new waveform information, and we'll also see some text on the IntelliRupter and the operation screen of the Intellilink software here. So let's go ahead and initiate that fault now. So you can see a pickup and a fault pulse closing that's occurring on phase A, and we now see that the IntelliRupter is actually reclosed all 3 phases. Here we can see the runtime plots have updated, and we can see the entire sequence of events. So what I'd like to now do here is go through this sequence of events step by step so that we can understand what happened and what went on. So let's start at the very beginning of this plot here. And this was actually the time before the fault was initiated. So this is what you might consider to be the pre-fault conditions. So in the pre-fault conditions, we can see both the source and load side voltages are normal, and we only have the load current flowing through the breaker. There's no fault yet here, and all three phases of the breaker are closed. Next, what happens is we push the button, and when we push the button, this LG FLT signal goes high, and we subject the system to a fault. So if we zoom in and have a look here, we can see once this signal goes high, we notice that the phase A voltage on both the source and load side becomes depressed, and we can see that the current, the phase A current through the breaker increases substantially, and the fault is sustained for a number of cycles here. Okay. Eventually, the IntelliRupter detects that there's a faulted condition, and it issues these open commands for each of the phases in order to operate the breaker. This is the initial trip command coming from the IntelliRupter. So we see once the IntelliRupter trips the breakers, we can see the current through the breakers all goes to zero. We no longer have any voltage on the load side of the breaker. Now, after the initial trip, 0.2 seconds later, the first pulse closing test should occur. And that's what we can see over here. Okay, so here what the IntelliRupter is doing is it's sending in close and open commands in order to close and open the breaker at a precise point on the voltage wave here. Okay, so it's closing and opening the breaker at a very precise point on the voltage waveform here in order to generate these pulses. So you see the first pulse here with the current flowing in the positive direction, and we see a second pulse later on where the current flows in the inverse direction or in the negative direction. So this is what we refer to as a pulse and the inverse pulse. So the IntelliRupter uses these pulses and performs some analysis to determine whether or not the fault is still present prior to reclosing the breaker. Now we can see after these pulses, the breaker remains open, so clearly the IntelliRupter must have determined that the fault is still present and that it should not reclose the breaker. Now that's the correct action because we can see this LG FLT signal is still high, so the fault is still present. Okay, now next we can see our test 1 occurs here. Our fault duration here is 1 second, so at this point here the fault elapsed and the fault is no longer present. Now 1.8 seconds after test number 1, test number 2 should occur. So let's have a look at the results, the pulse closing from test number 2. Here we can see the pulse closing results from test 2. So again, the IntelliRupter is closing and opening the breakers in order to generate the necessary pulses. So we can see here the first pulse, and then later on the IntelliRupter actually reclosed phase A. So once the IntelliRupter performed the pulse analysis on this first pulse, it must have been able to determine that the phase A is no longer faulted and that it's safe to reclose. This is the correct action because the fault has already elapsed and the system is, or the line is no longer faulted. We can see a similar type of action taking place for phases B and C. So we see a pulse close occurring on phase B. It performs a pulse analysis, determines the line is no longer faulted, and closes phase B. Similarly for phase C. So over here we can see that all three phases have been reclosed. The source and load side voltages are back to their normal conditions and the normal load current is flowing again. and power has been restored. Okay, so that's the story as viewed from these plots in Runtime here. Next, what we can do is we can go in the Intellilink software and we can have a look at the logs that were captured by the IntelliRupter. So let's do that now. You can go to the Logs tab here. You can see that I have it to capture the logs with only this EVT event category. So now if we go over to the historic log here, we can view the logs that were captured by the IntelliRupter. So you can see this is the moment at which the event started, and down here is the end of the event. So let's just have a quick look through these logs to see exactly what happened. So the first thing we see is that the IntelliRupter is detecting there's a current above the cutoff, and the protection elements are entering the timing state. So these are the time overcurrent elements that are picking up and beginning to time. Okay. If those overcurrent elements time out, eventually they reach the trip state, and at this point it'll log the fault voltages and it'll perform that overcurrent trip. So it'll trip all three poles, all three breakers. Okay. After all three poles are open, make some logs of the fault current, and then it'll move on to the next operation in the test sequence. Now that should be test number 1, which is a pulse close test. So here we see the start of the pulse, and it's closing and opening the phase A breaker in order to generate the first pulse. Perform some pulse analysis on that first pulse, and it determines that the line is still faulted. So then what it does is it proceeds with the inverse pulse. So again, it closes and opens the breaker in order to generate the inverse pulse. And again, it still determines that the line is still faulted. You can see that here. It says pole still faulted. So it keeps the breakers open, and then it'll proceed on to the next test here. So that's test number 2. Now, test number 2 is delayed enough that our 1 second fault duration is already elapsed. So again, we see here, it'll close and open pole 1 in order to generate the first pulse. Here we see it performs the pulse analysis and it now declares that the line is no longer faulted. It's now unfaulted. So once it senses that phase A is no longer faulted, it decides to reclose phase A. And then it proceeds onward to perform this kind of pulse closing for the other 2 phases, pulse 2 and pulse 3. So here we can see the first pulse for pole 2. Again, it performs the analysis and determines that the line is unfaulted, and then recloses the breaker. Similarly for pole 3, after which the breaker is reclosed and the power is restored. So again, on the Intellilink screen, we can see the nominal voltages and currents, much like we do on the meters of the runtime simulation here. So that concludes the demonstration with the IntelliRupter. I hope the demonstration was useful, and I hope you learned something. Thank you.
All right. Thank you so much, Christian, and thank you to our audience for joining us today and for your attention. We have some good questions to go over here in the Q&A, and I just want to reiterate a couple of things that came up in the presentation before we get to some questions for Christian. One, this case is fully available and it's fully documented in RSCAD. So if you're an RSCAD user, you can find this in the samples directory. And the documentation actually explains not only the Omicron interface, but also the Doble interface. So both of those options are explained in there. So feel free to take a look at that. We also had a question about whether multiple distribution models can be interfaced or whether distribution feeders can be interfaced with a regular model. And that's a good question. Traveling wave lines are not available in distribution mode. So the idea is that this is one tightly coupled subsystem that can't be broken up into multiple subsystems. So if you wanted to interface a distribution mode model with a regular one, you're not able to do that directly. So you would have to bring that distribution mode model into regular simulation mode, potentially do some reducing, and then interface it that way. A question for Christian. We have a question regarding the interface. Are you able to test the control module while operating the overhead switch? Christian, I think it might be good to talk a little bit more about the laboratory interface and the fact that we're not testing the actual full switchgear.
Sure. Yeah, so if you remember during the presentation, there was a slide early on where I had provided an overview of the IntelliRupter hardware. So that showed the IntelliRupter hardware mounted to a power pole, and there was also a large stainless steel base that's mounted to the pole on which all the equipment is mounted. So that includes all the equipment like the voltage sensors, power modules, and so on. Now, connected into the base of that equipment is that control module. Okay, so that control module we actually removed from that assembly to use it in this testing. So that control module, instead of being connected into that base, gets connected into the IntelliRupter test interface unit. And then again, the RTDS will inject signals into the test interface unit to test that the settings, protection settings on that control module. So that control module is no longer connected to that other hardware that the IntelliRupter would normally operate. So that other hardware, like the switches, wouldn't be operating when we're testing the IntelliRupter with the RTDS.
Excellent. Thank you, Christian. Another question about the interface here from Hossein. How are you able to measure the pulses from the Recloser controller and bring those back into the simulated environment? Was there a GTAI in the loop?
Okay, so this is another question about the hardware interface between the IntelliRupter and the RTDS. So just a recap on that, there's two I/O cards that are used at the RTDS to create the interface through the IntelliRupter test interface unit. In this case, the Omicron RI-R1. So the analog output cards, the outputs from that GTAO card are sent into the LL out 1 through 6 and 7 through 12 ports on the Omicron test interface. And that's what allows us to eject the analog signals for things like the voltages on either side of the breaker, and also the Rogowski coil output voltages, which are providing measurements of the current flows through the breaker. Okay. There's another cable that connects into the Omicron RI-R1 interface, and it's a binary inputs and outputs cable. Okay. That cable is connected to the GTFPI card, or the front panel interface card of the RTDS simulator. Okay. And it's that card, the GTFPI card, that actually exchanges the binary inputs and outputs with the test interface and with the IntelliRupter. Okay. So when the IntelliRupter is sending commands to the RTDS to perform things like the pulse coding, those pulses, those binary signals, are being sent out of the Omicron RI-R1 and brought into the RTDS using the GTFPI card.
Thank you very much. We have another good question here from Robert. Can the solution be scaled to test a full distribution automation system, like a source restoration scheme? And the answer is yes. This is a very scalable solution. That's one of the advantages of closed loop testing, is the inclusion of multiple devices in the loop. We have a customer that's doing testing of about 20 different distributed controllers right now, so that kind of scaling is definitely possible. And that scaling comes through the actual processing hardware in terms of licensing more cores on the simulator, increasing the size of the system, and also in I/O. So the I/O that Christian was using in this demo is on modular cards, and you can increase the number of channels that are available by connecting additional cards to the simulator. So the answer to that one is yes. Okay, we have another question here from Jose. Is it possible to test Flizzr schemes, which involve several IntelliRupter reclosers with this RTDS? From my perspective, I'll just say that Flizzr in general is definitely an application. That customer I was referring to with the multiple controllers, it's a Flizzr scheme that they're testing. Christian, I don't know if you want to comment a little bit on multiple IntelliRupter testing and what that would involve.
I think if you want to do testing with multiple IntelliRupters, then what the IntelliRupters need to do is communicate with each other. So I think what that would also involve is connecting the communication modules of the IntelliRupters into the docking station. So that information wasn't shown here, but it is possible to connect the communication modules into that docking station as I'd shown. And then you'd have to figure out how to get the various IntelliRupters to communicate with each other in order to perform this kind of testing.
Excellent, thank you. I think that wraps up our open questions. We'll stay on for a minute here to see if any additional ones come in. But I want to thank everyone again for your participation. Our next in-house webinar is going to be related to RSCAD FX. So as I mentioned earlier today, if you haven't checked out that teaser video, I definitely recommend it. If you're a user of the RTDS Simulator, there's some really exciting new features that we're rolling out. And the next webinar registration is not available yet, but if you're on our mailing list, you will be apprised as to that. And it looks like we don't have any more questions, so I will close the webinar. Thank you so much. Christian, thanks so much for your presentation today.
Thanks, everybody. Have a good day.